Alright, so vectors and dot products. First thing that we want to do is define what a dot product is. Then we're going to look at how it's used, some properties related to it, then how it's used, and the number one application that we're going to be developing here is finding the angle between vectors. So that's kind of where we're building throughout the day here. Alright, so first of all, let's talk about what a vector, or I'm sorry, what a dot product of two vectors is. Okay? The dot product of u and v is given by u dot v equal to u1 times v1 plus u2 times v2. Alright, where u1 and u2 are the components of vector u, and v1 and v2 are the components of vector v. By the way, the dot is significant here. You don't do vector multiplication by just not putting anything, because there's actually two different kinds of multiplication when it comes to vectors. Well, three if you include scalar multiplication of vectors.
You need the dot after the 2
So,
or the period?
The dot between the u and v, okay?
So the dot after the 2 is a period.
Yeah, that's a period.
Okay. That'll count.
Okay, u dot v, the dot here is significant because there's also what's known as cross multiplication, u cross v, and that's something totally different. Okay. No, we're not gonna get to that. So, anyways, someone put this formula in your own words.
The x component of u times the x component of v plus the y component of u times the y component of v.
Okay?
So if let's say like u and v are two different vectors, right?
Yes.
So if you multiply them, why would you get one thing? Right, because you're adding.
We're adding, so actually what do we end up getting here? Do we get a vector?
No.
No, we get a number, right? We get a scalar.
Because like, yeah.
Yeah, well that's how this multiplication is defined, okay?
So that's why it's different from the other one, because the other one you get like.
Yeah, the other one's totally different, yeah.
Before then.
When we multiply a vector by a constant, we get a vector. When we multiply a vector by a vector using the dot product, we end up with a scalar, okay?
I feel like it uses a formula we've already learned, but I can't remember the name of it. It's similar to.
It's kind of like when you did vector addition. You added the x components, you added the y components, but you end up with a vector. But here, you're multiplying the horizontal components, you're multiplying the vertical components, and then you're adding them together, alright? So let's practice a little bit, and I'm going to try to mix in the various kinds of notation, just for some extra practice with the notation as well. So here we have two different problems, both with vectors. Well, let's look at how this would work. We have the vector 3, 5 dot vector 6, 2, 6, negative 2. So I'm going to take the horizontal components, 3 times 6, and I'm going to add to that the product of the vertical components, 5 times a negative 2. Okay? So I have 18 plus a negative 10, which gives us 8.
Oh, it's negative.
Alright, so the product of your horizontal components plus the product of your vertical components. Again, different notation, but we're still dealing with vectors here. We have 3 times a negative 8 plus 9 times a negative 4. So we have negative 24 plus a negative 36, negative 60. Okay? So, dot product here is 8, the dot product here is negative 60.
Okay.
Okay?
This looks too easy. Where's the catch?
Yeah, that's what I
It is pretty easy. Well, the nice thing is this is just a part of finding the angle between two vectors. Okay? The nice thing is the rest of that formula that we're gonna look at, you already know how to do. So this is just kind of the missing piece. It is an easy thing to do, alright? Yes, I mean,
What would a dot product calculate by, like, what would it be necessary?
it's part of the formula that we're gonna look at down here, oh, not that one. For the angle between two vectors. Okay? So that u dot v over magnitude of u times magnitude of v is gonna equal the cosine of the angle between vectors. So that's what we're building towards here. Okay? How about if you practice with a couple of these, okay? Again, some different notation, but they're all vectors. Go ahead and find the dot product of those.
Good reasons.
Apparently Meep had a really big role in season 5 of American Horror Story. Yeah, he was gonna have like a really big
That's
role.
horrible.
Again?
It was a person.
Don't worry about it. Let's focus on dot products, okay?
There's someone who died inside the end. Never heard of it.
It's more than that. So much more than that.
The only reason it's more than that is because
Stop talking. Just stop talking. You're so insensitive, it's just stop.
Alright, let's look at our first one here.
Citizens, like,
What do we get for our first dot product here?
What's the negative 22?
Negative 22,
yeah.
okay? So we have 4 times negative 7 plus 6 times 1. So you have a negative 28 plus 6, and that equals a negative 22. Okay? Good. Any questions about that? Anyone not get that? Alright. How about this one? This one might be the
17.
one that might be easy to mess up a little bit.
17.
Okay? So you do negative 5 times 11 plus 6 times 12. So negative 55 plus 72. And like Thomas said, we get 17. Okay? Alright, so that's how to find the dot product. And there is no catch. That's it. Okay? I do want to look at some properties though of the dot product. Okay? First of all, notice on all of these, u, v, and w are vectors and c is a scalar. Okay? But here, if we have u dot v that equals v dot u, what is that an example of?
Cumulative.
That's, yeah, that shows that for the dot product, the commutative property works, okay? Remember we said that if the order doesn't matter, then the commutative property, that is the commutative property. We know it works for regular numbers. We showed it worked for vector addition. Now we know it works for the dot product as well, okay? Secondly here, we have the zero vector. Yeah, the zero property. Okay, the zero vector dotted with any other vector is going to give us the scalar 0. Okay, so note here the zero vector would be 0, 0. If I dot that with any vector AB, I'm going to get a scalar 0. Okay, it's a little hard to tell, but this is bold 0 there. That's the zero vector. Alright, so that's an easy one there. The third one, u dot the quantity v plus w equals u dot v plus u dot w. What property is this?
Distributive.
That's our distributive property, okay? distributive property. Okay, that's our distributive property. So you can add the vectors first and then do the dot product if you want, or you can just find the dot product of u with each of those vectors in the parentheses and then add the two scalars together. Okay, so it's kind of up to you. Alright, next one. This is a property we'll look at a little bit closer here, but the dot product is always going to equal the magnitude squared. Okay? Now, this one I want to take a moment with. Alright? Let's say that our vector v is the vector AB. Okay? If I'm finding the magnitude of v, what's that going to equal?
Square root of a squared.
Yeah, square root of a squared plus b squared. Okay? Well, let's think about this. If I had v dot v, I would be doing AB dotted with AB. Well, what do you get when you...
A times A plus B times B.
Yeah, A times A plus B times B, which is our A squared plus B squared. What would I get if I squared my magnitude?
A squared plus B squared.
A squared plus B squared. Okay? So here's something that relates our dot product to the magnitude of a vector. Okay?
Whatever you got.
Then we have the last one here.
It's different, but
Notice C here is a scalar. The scalar C times the dot product of u and v will give us the same thing as if we did C times one of the vectors and then did the dot product. Okay?
so half distribution.
Yeah, and it's actually, this is actually similar to a different property where the grouping didn't matter.
Associated?
Yeah, our associative property. Okay? It's, and again, these are not technical terms, well, at least for this one. It's not technically called the associative property, but it's similar to the associative property, where you can multiply one of those vectors by the constant first and then do the dot product. It also works in the other way, which we'll see in a moment here, okay? Here's an example. We have u dot v times w, and here we have u dot 2v. Okay? We're going to kind of do both of these problems at the same time. Because according to this property here, I could take letter b here and I could rewrite it. And I could take the 2 and separate it from the dot product. Okay? See how I did that? This is just like I started with this and I rewrote it like this.
It's definitely the dot product for like A. The dot product of u plus times v is a scalar, so you just do.
Yeah.
Okay.
Yeah. So here, I could find u dot v, and then I would only have to do that once, and I could use it in both of those. Alright? So if I do u dot v, I have negative 1 times 2, which would be a negative 2, plus 3 times negative 4 is a minus 12, so that gives me a negative 14. A negative 14. So now, then you what?
Never mind.
What were you gonna say?
Then you multiply, I don't know,
Not like
some things.
One.
Yeah, that's negative 14 times w, right?
Yeah, that had
How do we do that?
Oh, you just multiply by 2. Because
Like,
that's
look
B.
at by 14. Like,
We multiply by the negative 14. Yeah, now we're back to that constant multiple. Negative 14 times 1 is negative 14. That's our horizontal component. Negative 14 times negative 2 is a positive 28. Okay? So we found the dot product once. Now we plug it in here. And then we can also plug it in here. 2 times a negative 14 would be a negative 28.
Could you do,
You do 2v and then do the dot product of what you get from that.
Yes, you could.
Okay.
yeah.
You would get the same thing. 2v would be 4 negative 8.
Yeah.
And if I did that dotted with negative 1, 3, I'd get negative 4 minus 24, which is also negative 28.
Wait, why
Okay.
do you get a vector for the first one and a scalar for the second one?
Well, because notice what we get as a result. The dot product gives us a scalar, and we're multiplying a scalar by a vector, right? So when you multiply a scalar by a vector, you get a vector. But here, you're multiplying, well, in the end, it's really just a dot product. The dot product's going to give you a scalar. Okay. And by the way, part of the homework that I have on the website, part of that homework, there are parts where they give you an expression, they ask you to tell, is the result going to be a vector or a scalar? And just getting you to think through those things is helpful. When you're approaching a problem, that's something that's important to recognize. Should my answer be a vector or should it be a scalar at the end? Yes.
But in A, like if you use the distributive property, it would be wu or w dot u and or if you use the distributive property, wouldn't it end in a scalar and not a vector?
Well, note the difference here. The distributive property says that we're doing the dot product of a sum with another vector. We don't have a sum in the parentheses here.
Oh,
Okay, we just have a dot product. It's kind of like the difference between, and that's why I liken this to the associative property. It's kind of like the difference between if I had 2 times 3 times 4 versus 2 times 3 plus 4. Okay, here I'm going to distribute. Here I would just multiply the 3 and 4 and then double it. Okay, so that's kind of like that. This is kind of like this. Okay. All right, let's take a look at another one here. It says the dot product of u with itself is 5. That means u dot u equals 5.
Root 5.
How does that relate to the magnitude?
Magnitude squared.
That's our magnitude squared. So the magnitude must be
Square root of 5.
square root of 5. Okay? So again, just using that property. Okay. All right, so let's get to what the main emphasis of the lesson today is, and that is finding the angle between two vectors. First of all, let's look at what angle we're talking about. Okay? Note that here I'm finding the angle between u and v. However, different than vector addition, these vectors are both having the same starting point. Okay? We're moving them together so they both start at the same point. So here's vector u, here is vector V, okay? They both started here, and we're finding this angle right here, angle theta, okay? Now, it does represent this opposite side as V minus U. We don't need that. However, that does kind of give us a hint as to how this formula was derived. How do you think we derived this formula?
Well, the magnitude of V times magnitude of V, that's two side lengths. So it's like,
Law
I don't know
of
what it goes.
If we knew
I was thinking
what?
the area.
law of sines.
Log cosine.
Well, cosines, that's how we would get cosine of theta. Now, it would take a bit of working to get the law of cosines, but, and we're not going to do the whole derivation here, but that is kind of how it's derived. We have this opposite side v minus u, and we would just make u be the vector AB and v would be the vector CD, and then we would figure it out. But all you need to know is our formula, okay?
Is there a dot in between? Like, are you multiplying the magnitude of u and the magnitude of v?
You are multiplying the magnitude of u and the magnitude of v, okay? They don't write it there because those are both scalars, right? Once you find the magnitudes, you're dealing with two scalars and you're just multiplying them, okay?
So
So, you need to find three things, and then you can plug it into our formula to find the actual angle, okay? Yeah.
how, I don't understand that triangle over there. How does that side equal V minus U?
Because we would have to take, let's see, if we took this vector u, let me do it this way. There's vector u, and here is vector v, okay?
Yeah.
If I did a v, and then I did, whoops, this right here would be v plus u, right?
Yeah.
Well, if I wanted to do minus u, I would go like this, right?
Yeah.
So that would give me this vector right here, which would be v minus u, right? So that's v minus u,
Makes sense.
okay? Well, look, it's right there, okay?
Thank you.
So they just gave it to you rather than showing it all, but that is how we would get it.
But like, that's not really necessary because we're just trying to find theta, right?
Yeah, we're trying to find theta. Oh, let me put this back here. Okay. But anyways, that is significant, and if we're trying to derive this formula with the law of cosines and whatnot, okay? Well, let's go ahead and actually find the angle between these two vectors. All right, we have the vector u that's 4, 3, and I drew that here. And then we have the vector v that's 3, 5, I drew that here. So we know our angle actually should be what?
Between less than 90 degrees.
Yeah, we know it's going to be an acute angle, all right, just by looking at it. So we find the dot product. U dot v would equal what in this case?
27.
Yeah, 12 plus 15 would be 27. So I know the cosine of theta is going to equal 27 over, then we need our magnitudes. What's the magnitude of u?
That's 5.
Yeah, square root of 25, which is 5. So we know the cosine is now 27 over 5 times something. What's the magnitude of v?
Square root of 34.
Square root of 34, 9 plus 25. And you can leave it that way. Do not round. just leave it as the square root of 34. And then how are we gonna get what theta actually is? Inverse cosine, okay? Now you guys know arc cosine or inverse cosine will always give you an answer between 0 and 180. Okay? Which is good because our answer will always be between 0 and 180. If you're asked for the angle between, it'll always be less than 180 degrees. Okay? It'll always be between 0 and 180 degrees.
No, but
Okay.
it cannot equal 180.
They could if they were opposite vectors. You would get a cosine equal to -1.
Yeah, but you won't have a triangle then.
You wouldn't.
Yeah.
But that would be, we don't care about the triangle, we're just trying to figure out the angle here,
Okay, yeah.
okay? What I'm saying is, you're not gonna give this angle out here,
Oh, yeah, yeah.
okay? We're not gonna give that one. What?
Can it be 0?
It could be 0. If it's 0, then, if it's actually 0 or 180, we know the two vectors are parallel. Yeah. If you have parallel vectors, you're gonna get 0 or 180. Because we said parallel vectors could have the same direction or opposite directions. But what do we get in this case? Theta equals, come on,
The inverse cosine.
inverse cosine of 27 over 5 root 34.
It says an error.
22.16.
Why? 26.
So 22.2.
Yes.
If you got an error, it's probably because you didn't put parentheses around your denominator.
27 divided by 5 root 34.
Do five.
Oh, because it like, can you,
Because it's trying to take the inverse cosine of 5 and 2/5, 27 fifths, and then multiply that by root 34.
But I put the root 34 under, but then when I do another parenthesis, it won't.
So, where's your backspace? Get the right error to get out of the
Okay.
radical, and then do that.
and then
And then
another one.
Yeah, there you go.
22.
Alright, did everyone get 22.2? Does that make sense? It's actually a pretty simple formula, it's just a matter of remembering the formula. It's simple to use, it's just a challenge of remembering it correctly. Okay? Now think about cosine real quick, one last thing. If cosine is positive, we know our angle is going to be
Positive.
In the first
Low
one.
90.
in the first quadrant, there we go. So it's going to be an acute angle. If our cosine is negative, we know it's going to be
Third.
Not
in the
in.
second quadrant, it's going to be obtuse. So we aren't going to worry about the third or fourth because we want the angle between the vectors, not outside. Okay? What if the cosine equaled 0?
Then it's 180.
No?
90.
90. What in the formula would make our cosine equal to 0?
The denominator.
Oh, the denominator being 0.
No, not the, that would make it undefined.
The numerator.
The numerator being 0. So if the dot product is 0, we get a 90-degree angle, right?
Yes.
That has a term. That's what we call orthogonal vectors. Okay? Orthogonal vectors have an angle where theta equals 90 degrees. Okay?
Isn't it like perpendicular?
They are perpendicular, yes. Okay? So it's 90-degree angle.
Us, and then that's
Did it end at 205?
Is it 205 or 210? Because it's 40 minutes.
I got
It's 205.
204, but.
It's 205.
Alright, anyways, real quick, let me just mention this. This relates to slope. If you did the dot product of two orthogonal vectors, you would see that you've got the opposite reciprocal slopes, which is what you learned back in Algebra 1 made perpendicular lines. Okay? So that's it. We'll go over more of that tomorrow. Alright? Alright, see ya.
grammar works that took the entire class period and still didn't finish. Mainly because I wasn't really doing it for half the time.
Alex, I finished it in 10 minutes.
You next week.
Alright.
Well, it's easy. It'll take. Alright. See that?
等你们 retake 之后才。对，应该定不会找我。这个是橄榄球队的
会的，
丁是我的教练，
会的。
他前面刚看到我在训练，他刚跟我见面。耶！是吧？这是他们。他说只要在下课前穿上衣服就行。哎呀。
over C. This is a slope of D over C. We flip these, we have D over A equals negative C over D. Okay, this has a slope D over A.
Look at this so
That is the opposite reciprocal.
Excuse me, Mr. Dixon.
Hang on one sec. Slopes.
Hopefully we'll get lots of homework today.
What?
Alright,